I'm Anna Nora Evans. This is a presentation of my work with Professors Mary Lou Sofa and Brad Campbell on the use of Rust by software developers. Rust is a programming language that is designed for highly parallel system applications such as the servo browser engine. Rust helps programmers write memory-safe and data race-free programs using a novel type system. However, for Rust to be useful and suitable for low-level and real-time applications, it must be as fast as C. Thus, Rust aims at being safer than C, not necessarily safe, and as fast as C. Graydon Hoare called Rust's approach to safety pragmatic safety. The language contains a mechanism that allows a programmer to write programs that cannot be statically checked for safety. The mechanism is an annotation of the code that breaks the static rules. Finding the annotated blocks in the dependencies and checking for yourself that they are indeed safe is a daunting challenge. In code annotated to unsafe, the programmer may use additional operations that cannot be statically checked. The code could still be memory safe and data race free, but we have to trust the programmer to do the right thing. And thus there are no static guarantees. However, it is necessary, unsafe Rust is necessary for device drivers implementing an operating system or even interactions with an operating system. The major goals of our research are to understand how often and what unsafe operations are used by the Rust developers and what is the impact of unsafe use on the static safety guarantees. A Rust project is composed of units of compilation that are called crates, and the Rust language itself comes with a very small set of crates or basic libraries. The core library and standard library, which is basically collections, I/O, and multi-threading primitives, and memory management. Everything else is available in a central repository called crates.io. We noticed that Rust has an explosive growth. In September 2018, there were about 19,000 crates, and today there are over 42,000. This is an example that will help us understand the difficulties of tracing unsafe code. Library 1 calls function bar of library 2. In library 2, we have an object that implements has buzz interface, and it could be either from library 3, which is perfectly safe, or library 5, which is potentially unsafe because the buzz implementation contains an unsafe block. The library dependencies is as follows. Library 1 depends on library 2, which depends on 3 and 5 in turn depends on 4. But there is only a couple of lines that we need to trace down and understand. To analyze the safety of all these functions, in the example, we start with the end of the call chain. The function cooks in library 4 is declared unsafe. The programmer plans to use unsafe operations inside. Library 5 contains function buzz, which is possibly unsafe. From the outside, it looks perfectly safe, but it does use an unsafe code block inside, calling an unsafe function. Now, in library 2 function bar can be safe or possibly unsafe, depending whether it calls buzz from library 3 or from library 5. And that in turn makes function 4 of library 1 safe or possibly unsafe. We executed a large-scale empirical study by analyzing the majority of the available Rust libraries at the start of the study. From these libraries, we identified a relatively small subset of about 500 crates that account for 90% of the downloads. The assumptions in our study are that the standard library functions are safe, unless they're explicitly marked unsafe, and the compiler-generated unsafe code is safe. To understand how unsafe independencies influences the safety of the Rust ecosystem, we define a function as possibly unsafe if it is a function with unsafe code present in its call graph. Since Rust has polymorphic and runtime polymorphism, it's impossible to determine precisely the call graph. Thus, we implement two analyses. Whenever we can't resolve a function call. In one analysis, we assume that it's unsafe, and in the other one, we assume it's safe. We found that less than 30% of all the crates have an unsafe block, while almost half of the most downloaded ones have unsafe present. Less than 20% of all crates contain a declared unsafe function, and it is slightly more prevalent in the popular crates at 40%. Fewer than 20% of the crates expose the use of unsafe Rust, but more than half of them are actually potentially unsafe. We further looked at the unsafe operations, which are dereferencing a sys-style pointer, calling an unsafe method or function, accessing or modifying a mutable static variable, and implementing an unsafe trait, and accessing fields and unions. We found that the vast majority of the unsafe operations are unsafe function calls. To further gain insight in what programming languages the unsafe functions are implemented in, we checked the abstract binary interface of the implementations. We observed that the majority of the calls are to Rust functions. Re-implementing C libraries in Rust will not help eliminate most of the unsafe. We determined that there was no significant change in the use of unsafe in the most downloaded libraries over 10 months period. However, the unsafe coding guidelines and the list of undefined behaviors are under active development, so that may change soon. To help developers write correct unsafe code and understand when unsafe code is used, we propose the following: a definition of a mechanism for defining pre- and post conditions for declared unsafe functions. The compiler should print a warning along with a call chain for every possible unsafe function, and we propose changes to the central repository. Every crate that contains unsafe code, it must be clearly marked. A dependency tree for each library should print which crates use unsafe in the dependency list, and to maintain a list of code reviews of any unsafe Rust. In conclusion, we executed a large-scale study and analysis of unsafe use in Rust software. We found that the majority of crates are not guaranteed by the compiler to be memory safe and data race free, and we determined that the most common use of unsafe is due to unsafe function calls, and we provided a list of recommendations to enhance the RISE compiler and the ecosystem.